In any synchronous digital design, data must travel from one register to the next within a single clock period. Timing margin is the difference between how long data takes and how much time the clock allows. When that margin shrinks to zero or goes negative, the chip fails. So margin is not something you fix at the end. It is something you intentionally manage across the full design lifecycle. The early phase is where you create margin, and it has the highest leverage. Think of it this way. A poor architectural choice costs you weeks at sign-off, whereas a good one costs nothing extra up front. A pipeline divides a long computation into stages separated by registers. The concept is simple. If a combinational path is too long to complete in one clock cycle, split it. But the key best practice is to balance those stages. If one stage has 200 logic gates and the next has 20, your clock frequency is bottlenecked by the slowest stage, and the faster stage wastes margin. Even pipeline depth matters. Deeper pipelines allow higher frequencies but introduce latency and complicate feedback paths. Now, clock domain crossings, or CDCs. Whenever data moves between two independently clocked regions, there is a risk of metastability. A flip-flop may capture a value that is neither a clean 0 nor a clean 1, making its output unpredictable. CDC structures, such as synchronizers and handshake protocols, prevent this, but they add latency and must be planned at the architecture level. Retrofitting CDC logic later is error-prone and frequently causes silicon bugs. On the clocking strategy side, clock uncertainty is important. If you do not budget for it up front, the tools will assume ideal clocks during synthesis and then hit you with violations once real clock models are applied. That is why we say to budget clock uncertainty early. It means telling the synthesis tool to assume the clock is less than ideal, so it builds in extra slack from the start. Regarding RTL practices, non-blocking assignments are essential for flip-flop modeling because they mimic how real hardware works. All registers sample simultaneously at the clock edge. Blocking assignments, in contrast, create sequential dependencies within an always block that can lead to simulation mismatches with synthesis, meaning your simulation says the design works, but the actual silicon does not. High fan-out means a signal must charge more capacitance, which slows it down and creates long paths that the tools struggle to optimize. Once you move into physical design, the game changes. You are no longer dealing with abstract logic. You are dealing with real wire lengths, real capacitances, and real signal propagation delays. The mid-phase is about preserving the margin your architecture created. Placement is fundamentally about proximity. The closer two communicating flip-flops are, the shorter the wire between them and the less delay it adds. Congestion is the enemy here. When too many signals compete for routing resources in one area, the router is forced to take detours, which lengthen wires unpredictably. A timing clean design with poor placement can lose hundreds of picoseconds of margin from routing detours. During clock tree synthesis (CTS), clock skew is critical. If the clock arrives late at the capturing register, it effectively borrows time from the next stage. This helps setup, but hurts hold. If the clock arrives early, the opposite happens. The best practice is to minimize skew so that timing analysis assumptions remain valid, and you do not create hold violations that are expensive to fix later. Now, the concept of fixing hold before setup during the mid-design phase, specifically post-CTS, a hold violation means data changes too quickly, corrupting the value being captured. It is a functional failure, not just a speed issue. A setup violation means data arrives too slowly. You can often fix this by reducing the frequency, but hold violations can occur at any frequency. When you fix hold by inserting delay buffers, those buffers consume area and add delay to the setup paths as well. That is why the order matters at this stage. If you fix setup first and then fix hold, the hold buffers may re-break your setup paths, creating an endless loop. This hold first strategy is critical during mid-design because the design is still fluid, and hold buffer insertions can have a large structural impact on setup paths. At sign-off, you make the final call on whether this design will work in real silicon across all manufacturing and environmental conditions. The focus is protection. You are no longer optimizing. You are ensuring robustness. Note that the order of setup and hold closure differs from the mid-design phase. At sign-off, setup is typically closed first because it determines whether the chip meets its target frequency. Modifications at this stage are small, targeted ECOs rather than large structural changes. Hold is closed afterward because hold fixes at sign-off are usually minor buffer insertions that are unlikely to disturb the already tightened setup paths, especially when adequate guard bands have been applied. This is not contradictory to the mid-design hold-first approach. The difference is that, at sign-off, the design is nearly frozen, and ECO-based fixes have a much smaller ripple effect. An ECO, or engineering change order, is a targeted modification made late in the flow, such as swapping a cell, adding a buffer, or rerouting a net. The danger of aggressive late ECOs is the ripple effect. Fixing one path can shift delays to neighboring paths, creating unexpected violations. This is why we emphasize local fixes over global changes. A guard band is an intentional extra margin beyond what timing analysis says you need, to absorb the unknowns that models cannot perfectly capture. PVT stands for process, voltage, and temperature, the three primary variables that affect transistor and wire speeds. Real silicon spans the full range of fast and slow corners, so you must analyze all corners to ensure the design works everywhere, not just at the nominal point. OCV, AOCV, and POCV are increasingly accurate models of on-chip variation because transistors on the same die do not behave identically. OCV applies a flat D rating to all paths, which is pessimistic. AOCV, or advanced OCV, reduces pessimism by considering path depth. Longer paths average out variation more. POCV, or parametric OCV, goes further by using statistical distributions. Enabling these ensures that your sign-off analysis reflects real silicon behavior, rather than overly pessimistic or optimistic assumptions. Finally, aging effects such as BTI, bias temperature instability, and HCI, hot carrier injection, cause transistor thresholds to shift over the product lifetime, gradually making transistors slower. On advanced nodes below 7 nanometers, this degradation can significantly erode your margins over a few years. Accounting for aging at sign-off means running timing analyses with degraded transistor models to ensure the chip still meets spec after years of operation, not just on day one. The key takeaway is that timing closure is not a phase. It runs throughout the entire design flow. The best part is that it is a shared responsibility across teams, with architects enabling it, physical designers preserving it, and sign-off engineers verifying it.